Hello everyone and welcome to this webinar titled How to Treat Soil Contaminated with Various Pollutants Using Thermal Desorption. I will be your host during this webinar. I'm Aurélien van de Kerkhove and I'm the manager of the Business Development and Engineering departments at Amherst Technologies. Today to present to this webinar, the guest of honor will be Jean de Rhône. Jean de Rhône is an engineer specialized in the sustainable management. He joined us approximately 6 years ago. He has a really interesting path at Amherst Technologies because he started as a project engineer. Then he had the opportunity to work on one of the biggest projects of Amherst Technologies for a big client, Noroxo, as a project manager. And 1 year ago, he had the wonderful idea to join the business development. Besides, I also would like to give you some curiosity details about him. That's an ultra runner. I still don't get it, to be frank with you, but last week he ran 100 kilometers in less than 15 hours. So he is definitely the most sportive guy of the company. Anyway, the main objective of this webinar is to address complex contamination into the soil and basically what's the logic behind it to remediate it with thermal desorption. The presentation will be divided into a few parts. Of course, a short introduction of the company. Then you will need some basis to understand it. So it will be the technology principle, and then we will jump on the core of the presentation, which is what is a cocktail of contaminants and basically what's the logic behind it to remediate it through thermal desorption. Before starting this presentation, some pragmatic information. The presentation will last around 30 minutes, and then we will have Q&A sessions of 10-20 minutes. Please feel free to ask all the questions in the Q&A part of this webinar or directly in the discussion parts. I will, because your micro is mute, I will just collect all those questions and I will ask him directly. You will also receive at the end of this webinar a certificate just about the attendance of this webinar. So once again, I'd like to thank you all for attending this webinar. And now I let the floor to Jean for this very interesting topic. Thank you, Jean.
Yeah, thank you, Aurélien, for this little introduction. I had the opportunity to run for 15 hours, so I think I thought a lot about this webinar. So I hope you will understand everything, because yeah, I had the time to think about it. So first of all, as Aurélien said, I will introduce a bit our company. So Amherst Technologies is a Belgium-based company with headquarters in Brussels. We provide remediation technologies all over the world since more than 25 years. And in order to be standalone, we have our own smart burner manufacturing facility. And we also invested in our own lab and research and development facility to develop new products and technologies. So like every year we develop new products, so that's pretty cool. Here are some names of partner or client that trusted us. So you might know Eni or ExxonMobil, and also some consulting agencies like AECOM or Golder. You can see on this slide that we operated all over the world with local partners. On the blue spots present ISTD, so in situ thermal desorptions, and the orange spots and red spots ex situ thermal desorptions, or you might also know the name thermopile. We also used to run in green rotary kiln, but we decided to stop this method in 2006. So now let's talk a bit about the technology principle. So as you might know, we are specialized in thermal desorption, but what does it mean? Thermal desorption is a physico-chemical technique that is used to vaporize organic pollutants through the heating of the soil temperature. So how do we do that? So first of all, we basically generate a flame. So here. So this flame generates heat, and the heat is conducted through two coaxial pipes into the ground, leading to an increase of the soil temperature. So once we get the vaporization of the pollutants, we can get them through vapor pipes that are connected to some fans, and that allow us to extract the pollutants that are vaporized. So once the flame is created, as I said, it will pass through two coaxial pipes, and the heat is homogeneously distributed through the heating pipes. So we can do that either vertically, so ISTD, yeah. ESTD, so it's a pollution that will be horizontal, so we build a thermopile, and we also can treat horizontally or oblique through ISTD. Once the pollutant gets extracted, the vapor extracted on the vapor phase. We extract the vapors, and we need to treat the vapors. So AMOS Technologies developed three main ways of treating those vapors. So the first way is reburn. So it consists in the injection of the polluted vapors in the heating tube to get thermal oxidation of this pollutants. It also decreases the total volume consumption of the fuel. We also can place vapor treatment units. So in case of complex pollution, we can use VTU. So it's an ad hoc unit, and we will send all the vapors to this unit. We also develop Thermoreact, which is an in situ neutralization. So basically, what it is used for, it's an in situ technology to neutralize acidic compounds in order to be less acidic for the networks of the vapor treatment unit and all the networks of the heating system. So now that you know a bit more about how we can treat those vapors and how we do that, I wanted to explain a bit what kind of pollutants we can treat. We can treat different pollutant family. So we like to group each compound in a family, as each family will have approximately the same behavior and the same chemical and physical properties. So we do not like to speak about hydrocarbons and benzene and etc., TC, DC, but we like to categorize them in some families, such as explosives, cyanides, semi-halogenated organic volatile compounds such as PFAS or PCB dioxins. We also treat mercury, organic volatile compound, or semi-organic volatile compound. So as you might know, because you all might work in the remediation strategies, each polluted site has its own history. So some of them are polluted with one single family. So for example, on this site, we had a site with two spots with a lot of hotspots inside those spots, polluted with a single family, which was halogenated compound. but we also can have other type of sites with where the historical pollution will lead to a multiple family pollution. So on this example, we had organic volatile compounds, halogenated volatile compounds, and PCB. So now that I talked a bit about what we can treat and how we can treat it, I will talk a bit more about the soil and the vapor treatments on a multiple family polluted sites. So first of all, sometimes it's very rare, but sometimes when the pollution is homogeneously distributed on the site, we might treat separately each compound. So for example, here we were able to build a thermopile, knowing that in the left part we had PAH, and in the right part we had PAH, and we decided to place PCBs in the middle of the pile because PCBs has the higher vaporization temperature, so we know that we will need to increase more the temperature of the soil to get rid of all the mass of PCBs. So, so we place it in the warmer place, and then we could decide on the temperature and the treatment time of each part. So the left part was 200 degrees for 2 days, the PCB's part 250 for 2 days, and PAH 200 for 6 days. So thanks to that, we were able to monitor the treatments for each part of the pile, so which is cool. And it led to a decision of stopping the left side that was the less impacted first, then the right side 9 days after, and the middle part 14 days after. So thanks to that, we could gain some fuel or some energy because we monitor only part by part. So it's possible to do that when the soil isn't mixed. But what can we do once the pollutants family are mixed in the soil? First of all, I wanted to define what is for thermal disruption worker a cocktail, because it might not be the same as for you. So when the soil is contaminated with various pollutants of the same family, like TC and DC, we do not say that it's a cocktail. Like, that's why I place water, because for us, those two pollutants have the same behavior. Maybe it's not exactly the same temperature that we have to hit, but they have the same behavior and we can treat them the same way. But what is for us a cocktail? It will be different families of pollutants that are mixed in the soil. So here, for example, COV, mercury, and TC. And for the expert, it makes wonderful spritz. Like it's a good mixture. It will be complex to treat, but it's a good cocktail. Yeah, you might find better cocktails, but spritz is one of the main that I know. So how do we choose for? First of all, we have to choose the temperature that we have to hit the soil. So we choose the worst case. So it's the worst pollutant is chosen to choose the target treatment temperature. The worst pollutants, I mean the most complex to vaporize. So in this case, you can see that there are hydrocarbons, so COV, mercury, and TC. So hydrocarbons, the total vaporization temperature will be from 180 to 250, the mercury 357, and the TCE 87 degrees. So we choose to monitor the mercury, we choose to take the mercury as the temperature to monitor, because we will monitor its desorption kinetics to set the temperature. So we don't have to reach 357 degrees to get rid of all the pollutants. We will reach less higher temperature, but I will explain that later. So now to understand what will compose the vapor, let's do a little tricks, like a mental game. So I want you to think about a soil contaminated with halogenated compounds. So we heat the soil and so there is 3 meters interdistance between each burner. We heat the soil and we stop after 30 days. So it's like D-Day, I will call it D-Day. So what's happening in the soil at this special moment? So this picture that is just here presents an above view of the soil temperature gradient. So here you can see after 30 days, the gradient of temperature. So here in purple, you can see that the heating tube is the soil next to the heating tube is at 450 degrees, but 50 centimeters away from the heating tubes around here, the soil will be at 200 degrees, and like 1 meters away from the heating tube, the soil will be at 80 degrees. So what I wanted to explain is that at each moment of the treatment, the temperature gradient and the temperature is moving. The temperature are different at each point of the treatment site. So you cannot say that okay, the temperature is at 100 degrees. No, it's not right. It would be at 100 degree maybe in the cold point like here, but here it will be at 300 degrees, for example. So at the moment we have different temperature on the treatment site, but what does it mean for the vapor composition? So I want you to still think about this site contaminated with halogenated organic compounds. Sorry. So this graph presents the capacity of each compound to go from liquid phase to vapor phase. So here you can see the temperature, so from 0 to 200 degrees, and here the saturation pressure, and here you have the atmospheric pressure. So we say that in our heating strategy, we are at atmospheric pressure. So the capacity of each compound to get vaporized evolutes in function of the temperature. So let's take the example of the previous slide. So we are after 30 days of treatment at 1 meter of the heating tubes, and the soil is at 80 degrees. What do we have as a compound in the vapor? So here on this graph, you can see that we have the vapors will be composed by many compounds. Like the main one will be benzene, that is here, but you will also have a bit of water, and you will also have this compound, and you will also have in a very little ratio this compound. Like all these compounds will be present in the vapor, but in different ratios. So the vapors will be composed by a lot of different compounds, but with different ratios. And these ratios evolve while the temperature evolves. So I still want you to remember about the other case. So now the temperature is not at 80, but at 200 degrees. We are 50 centimeters away from the heating tubes. What's inside the vapors? Is it the same that as 80 degrees? No, it's not the same. As you can see here, there are a lot more of this compound. There are a lot more of this compound, and a lot more of those compounds. So we will still have the same compounds, but not in the same ratios. So those two slides are pretty important to understand that at the same moment, the vapors will be composed by, in all the points, the vapors will be composed by the same compounds, but with different ratios. So you don't have like at 100 degrees, you don't have only benzene, but you have benzene, toluene, nitrotoluene, dinitrobenzene. You will have a lot of compounds. You don't vaporize for example, the benzene only at 80 degrees, but like at 50, at 40 degrees, we already have some vapors. And as we pump the vapors in the soil, each compound will get to our vapor treatment unit. At each moment, you will have in the vapor treatment unit a lot of compounds and different ratios going inside the vapor treatment units. So now that I explained you a bit about the cocktail in the vapors, so what's happening if we have a cocktail, what's happening into the vapors, I wanted to have a look on how we can deal with this cocktail of pollutants in the field. So I will explain that with a case study. So it's a case study of a site located in Gela, Sicily. So it's not the best place with the best beaches, but it's already nice to be in Sicily with the sun. The remediation was in collaboration with CIMAM and Icaro, which are two Italian companies, and it was done in a already working refinery. So I will show you two pictures of the site before the remediation, so don't get scared. We remediate everything, but so here is the place. So it was basically a dump of all the products. Yeah, all the refinery products were dumped in this place. So this was before the remediation, and this was already also before the remediation, where just before they tried to remove the most easiest, the easiest compounds to remove. Yeah. So we had many pollutant families, such as COV, halogenated compounds, and mercury. What is important to see on this table is that we have three families of compounds. So yeah, we have a nice spritz. It's nice because we are in Italy, so it's perfect. But what is important also to see is that we have high COV and COHV concentration. So here you can see the numbers, they are pretty high. But we also have mercury, but in a very low concentrations. So yeah, that's important for the next slides to remember. So what we did on this site, Amherst Technology took care of the thermal desorption, and Siemens and Icaro, they took care of the water treatment, and as well as all the general workers. They gave us general workers. So we basically took care of all the engineering part. And here you can see that we divided the site in two areas. So first of all, we remediated the inside of the dump area, if I can say. So here is one batch. And then we remediated all the surroundings. So yeah. So now the site is all remediated. As I explained previously, here is how we choose the treatment temperature. So we have COV, COHV, and mercury. So here are the vaporization temperature of those compounds. On the mercury, we do not have objective on mercury remediation, but as I explained before, it's not because we do not treat the soil up to 350 degrees that we won't have any mercury in the vapors, because mercury will vaporize once it gets to 50 degrees, for example. I don't have the real number, but it vaporizes very, very fast. So to choose what we could use as vapor treatment, here is a shame of what happened inside our brain. So yeah, now you are inside my brain. Well, not mine, but other engineers' brain. So we thought, okay, there is hydrocarbons, there are COV and COHV. We could do reburn, but there is also mercury, and there is also chlorinated compounds. So what can we do? We need to do a vapor treatment unit. We have to build our own vapor treatment units. So once you know that, what vapor treatment unit we need to build in order to get rid of all those pollutants. So here is a design of the vapor treatment unit, and here are some views from the above. So here was the entry of the VTU. So bam, 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 the vapors get through this way, and then they get to the chimney. So here is the same. Here. You don't see so much, but so the idea of those two pictures were to show that there are a lot of equipments in order to get rid of all those pollutants. Sorry. So the question was the type of vapor treatment unit, and what is the most acceptable vapor treatment unit to install? Because as you might know, vapor treatment units, they are it's a big installation, and they cost a lot. And yeah, so what to put in, what to place in this site? So the first idea was the theoretical design. So still, I want you to be in my brain. So we have a lot of COV and COHV, but we also have mercury. So the only way to treat everything in the vapor treatment unit is to condensate the vapors and to treat them through activated carbon with a sulfurage treatment to also treat mercury inside the vapors. So basically, it was not possible to get all the vapors in activated carbons because the site was very big and there was an enormous mass of pollutants. We treated for 3 years, I think, and we removed like thousands and thousands of liters of COV, hydrocarbons, everything. So, so this solution was not technically and economically sustainable. So then there was the second idea that we did not really have, but I wanted to place it in this slide because it was not really realistic. But we could have thought, okay, there is a very low mercury impact. We might not have to care of this impact, and only use like standard way of treating COV and COHV, so which is condensation and catalytic oxidation. But this is not possible because of atmospheric releases, and yeah, we do not want to have atmospheric releases in the atmosphere. So what did we do? We had a pragmatic idea, which was a mix of those two first ideas. So it was to treat the vapor in a standard way, like if there was nothing, no mercury. So this was called the standard operating mode. But while monitoring the vapors, the mercury concentration in the vapors at the entry of the mercury. So if there was any mercury trace at the entry of the vapor treatment unit, sorry, the vapor flow would be directly directed in a specific activated carbon to get rid of the mercury, and then it would also pass through the normal equipments to get rid of all the other pollutants. So this solution was technically safe, and thanks to that, we could have a risk management of the mercury. So now I just want to explain you a bit about what equipment did we place on this vapor treatment unit for you to have a better idea of how complex that is. So first of all, we needed to condensate all the vapors in order to collect the main contaminants in the condensate, or at least the most of them. So we had heat exchanger with vapor cooling from 150 degrees to 30 degrees or less. So could help to remove the water and the pollutant condensation to end the pollutants into the condensate. We also use the demister, so to catch the pollutants and water droplets, and as well as coalescing filters to eliminate water and hydrocarbons droplets. So those three equipments were pretty important and mandatory. As you might know, in activated carbons, they really do not like liquid stuff. So that's why it was really important to condensate as well the vapors. So here you can see the vapor treatment unit. So it's a PNID. So the vapors were getting air to air. And in blue, you can see the four equipments that I talked about. So the heat exchanger and the demisters and the coalescing filters as well. In red, I wanted to show you the vapors flow in a standard operating conditions. So it's getting air from air to air. There were also other equipment such as a catalytic oxidizer to help to have a COV reduction, and as well as a zeolite, like it's like activated carbon, so which was placed at the chimney to have the last removal. So here you can see in purple those equipments. So this was the Catox and this was the zeolite. So this is in red the normal operating the standard operating mode for the vapors. So it was getting from air. Sorry. Oops. From air to air to air, blah 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 blah, blah, and to the Catox and to the chimney, and then we had the atmospheric releases. So then let's talk a bit about the mercury measurement. So there was a mercury measurement through a sampling device. So this sampling device that we engineered, it was placed in the middle of the vapor treatment unit. It was helping us to have a lot of information about the mercury concentration at many points of the vapor treatment unit. So this sampling device was connected to a PLC, so it's a programmable logic controller. So it's like a big computer that gives order to some devices inside the vapor treatment unit. So here you can see a pictures. This is the VM3000 that is an analyzer for the mercury. So on this PLC, we asked the PLC which was connected to the VM3000. So if there was some Hg presence, so mercury presence at the entry of the VTU, the vapor flow was deviated to some activated carbon, sulfurized activated carbon. After 1 minute, if there was still some mercury at this point, at the entry of the VTU, the flow was still deviated, but then after 1 minute, there were no more mercury, for example, the flow was then deviated again to the standard way. It was important to do that because if we do not have a check every minute or every X minutes, the flow will be and it's flow that will activated carbon. So this activated carbon would saturate very fast because of the water and everything. So that was important to react once there is no more mercury going inside the VTU. We were lucky because mercury was not coming every time inside the VTU. It was depending on the batch and the places of the batch and the temperatures. So now I wanted to show you what is the difference between the standard and the non-standard mode. So here are the two gags of mercury. We had two in order, if one is saturated, we can pass through the other one. So it was done thanks to another measurement. So yeah, So here is the standard mode, but once there is mercury presence at the entry of the VTU, this compound, so it's an automatic motorized valve that is linked to the PLC. So the PLC asks the automatic motorized valve to close this direction and to open this direction. So the vapor flow will get inside this GAC, and then it will pass on other pipes, and then joining again the normal operating flow, getting to the catox and the zeolite, and be removed. So thanks to that, the vapor flow, the vapors can be treated with the standard equipments, but as well in the mercury activated carbon, so to treat the mercury. So now that I talk about everything, I wanted to conclude about that. So for the first point to remember is that the treatment temperature and time is when we have a complex spritz, a complete cocktail. It's done according to the most complex pollutant family. So if you have COV and mercury, we will address the temperatures thanks to the mercury vaporization temperature. But the second point is that it's not possible to split each pollutant from the vapors. So the VTU design needs to deal with that. So here you have the spritz. You cannot. You have a spritz. You cannot split the spritz from Aperol, so which is COV, then water, then Prosecco, and water. You cannot split every pollutant. You cannot split every pollutant from the vapors. It's really not possible. So what you have to do is just from a spritz, you need to build a vapor treatment unit in order to have some of the contaminants by the condensation, some by GACs, some by other techniques, and some by oxidations. So yeah, what is important also to learn and to remember is that in the vapors you have a big mix of compounds that are not easy to take care and to deal, but yeah, we need to do it, and thanks to the VTU and our engineering knowledges, we can do that. So thank you for your attention, and now I think it's time for a little game of questions.
Well, thank you, Jean. It was really interesting, this presentation, and I really like your conclusion. Basically, I think the two main messages of this presentation is when we deal a cocktail of contaminants, basically to address and to define target temperature is the most complex contaminants. And besides it, when you have a cocktail, you have to deal with the cocktail in the vapors. You cannot split it. So quite really interesting. We have a few questions in the Q&A. The first one is more about how to define the target temperature. It's how often do you do a laboratory test to confirm that a target treatment temperature will work for given soil and pollutant?
Yeah. So basically, we already have a lot of, as we have 25 years of knowledge about thermal desorption, we already know most of the pollutants and how they get removed and how they are removable on each soil. But sometimes it's very different if you have, like, for example, mud or very complex complex cocktails that we like. For example, if we have TCA, mercury, and everything, it's some cocktails that we never found. So if we have that, it's very interesting to do some laboratory tests. So it will be some kinetic test in order to define the treatment temperature, and in order to know, so okay, at 200 degrees I remove like 95% of the pollutants, but at 210 degrees, we remove 99%. So if we have very complex pollution of our media, we will ask the client to send us some soil and do some laboratory tests.
Okay, quite clear. I see we still have 10 minutes in front of us, and we still have many questions. So I will just pick a few of them, and what we will do, it's in the mail, we will address all the questions like that. You can have some written information. So the next question is, do you assume that the treatment is complete once all the cold points have reached the target treatment temperature? Or do you confirm that they are no longer contaminated vapor with a specific detector?
Well, yeah, once the well, we have two ways of monitoring, two main ways of monitoring the soil. If the soil is completely clean. First of all, we monitor the temperature. So as I explained, we monitor the temperature at the cold points. So yeah, normally, if at the cold point we reach the higher vaporization temperature, we know that there is no longer pollutants inside the soil. But in every places of the batch, you don't have the same temperature in the cold point. So what is important also to do is to do some hot sampling. So once the temperature is approximately the vaporization temperature at the cold point, we decide to go on site and to take some samples. So it's called hot samplings. Then we send it to some laboratory, and then we are sure that it's clean or not clean. If it's not clean, we can continue to hit the soil, and if it's clean, we can stop the treatment. So we do not just focus on the temperature, but also on some samplings.
Yeah, it's just so to summarize what you just said, it's basically the temperature is indirect information that will just let us know what would be approximately the progress of the treatment. But if you want to know exactly what's the concentration, the remaining concentration to your soil, the best way to do that is to take a hot sample. So basically, once we have, the average cold point temperature reaching target temperature, we trigger the hot sampling phase. Okay, other questions, Jean. In case of having a contaminated cocktail of volatile chlorinated solvents, hydrocarbons, and BTEX, should the vapors be treated by reburn or through a vapor treatment unit?
Can you just say
chlorinated
again?
Compounds, hydrocarbons, and BTEX.
Yeah. So yeah, I think we use the reburn if there is no chlorinated compounds or not any halogenated compound. If there are some, we can use the vapor treatment unit.
Yeah.
Is that okay? Yeah.
Yeah. So basically, the plan is when we do a reburn, what you will get, you will re-inject directly the vapors through the burner bodies, and at the outlet of the heating tubes, you will get CO2 and H2O. But if you have chlorinated compounds, you cannot break down the chlorinated atoms. So you will release it into the atmosphere, which is quite an issue about the standards. So it depends, of course, on the concentration. If the concentration is really low, we can still think about using the rebirth. But just by reading your questions, as just Jean said, we should go for vapor treatment unit, just to make sure that we meet the standard of the stack.
The risk is also to create more complex compounds by if we use reburn, we have thermal oxidation, so maybe with chlorinated compounds, it can create other secondary compounds that will be more risky, even more risky. So yeah, definitely not a good idea to use reburn for that.
Yes, I'm just looking at the questions. Just maybe one last question, but there are so many questions, which is really good. So it means it was a good presentation, Jean. I will take. Okay, here it's one of them. What are typically the treatment times in situ and ex situ for common contaminants like TPH and chlorinated solvent?
Yeah. Okay. So the time. So the timing. So
Yeah,
the timing.
duration, yeah, totally.
The duration. Yeah. The timing will depend on many factors. First of all, water presence in the soil is one of the main factors because, as you might know, the longer phase of thermal treatment will be the increase of the soil temperature from 0 degrees or 10 degrees to 100 degrees because we need to evaporate the water. So if we have a lot of water inside the soil, it will take a lot of time to get rid of this water, and then it will take more time to get rid of all the pollutants. So this is one factor, but we are it also depends on the client strategy. Like if the client wants to be very, very, very fast, we can place all the burners very close. So we change the interdistance. So in a standard way, we place the burners at 1.5 meters from each burner. So there is one burner, then 1.5 meters away, another, and another, and blah, blah, blah. So this is the standard way. But if you are if you have less time, we can just place them like at 1 meter, and then it will be faster. But so if I can answer the question in a standard way, if we have like 15 degrees of in a normal soil, normal way, so with 15 to 20% of humidity in the soil, and with hydrocarbons in the soil, the treatment can take from 35 days to 50 days. Yeah.
Okay.
So it's very standard. So this question cannot be really answered like that. We need more.
Yeah, it depends on the interdistance between the heating tubes. So just a last questions, which is quite related to this one is, which soil characteristics determine the spacings, so the interdistances between the heating tubes?
So the soil characteristic that we need, it will be the porosity of the soil, and as well as the humidity of the soil and the density of the soil. Thanks to those three parameters, we can address what is the interdistance and how many times it will take to remove pollutants.
Yeah. So basically, those three parameters allows us to do some the design engineering stuffs, but basically the main driver to define the spaces, the spacings between the interdistances is definitely what's your time constraints. Is it 2 months? Is it 6 months? Is it 7 months? And based on this one, we can define what's the financial optimum based on your time constraint. Well, I think it's time. It's already been four more extra minutes, so I think it's time to close this webinar. There are still many unanswered questions, so you will receive this afternoon all the questions of all the of those answers. And once again, I would like to thank you all for attending this meeting. I hope you will keep those two really good information with the cocktail, which is we have to take the most complex one to determine the target temperature, target kinetics. And when you have a cocktail of contaminant, you have to deal with the cocktail of contaminant in the vapors, in the vapor treatment units. So Jean, thank you for
Thank
this
you.
presentation,
Thank you.
and you will get you can see this presentation on YouTube. It will be probably in the afternoon, and you will receive the certificates.
I did not say, but you don't have to abuse of spritz because yeah, normally I have to do a disclaimer about that. So
Anyway, thank you all
thank you.
for your time. Have a good afternoon, a good morning.
Bye.
Bye.